Buonasera a tutti, benvenuti in una puntata della Peritech di Torino NET Meetup in compagnia di Codemotion che ci ospita anche oggi sui canali, e ricordiamo che su Codemotion potrete rivedere poi la replica di questa puntata. Oggi parliamo di una roba strana, insomma, trasformare ciò che scriviamo come softwareisti in chip del computer. Ok, sembra una roba incredibile, ma è una cosa possibile. Scrivendo codice in .NET. Non ne parlo io, ma introduco un ospite internazionale, ok? Quindi è Zoltán Lehóczky, che ho sempre paura di come si presenta. Quindi da qui in poi switch in inglese e aggiungo il nostro ospite. Buona visione a tutti. Hi Zoltán, welcome here with us also tonight. Zoltán, can you hear me?
Yes, hello.
Oh, perfect. Hi, Zoltán. Welcome here. Tonight, I think that will be something magic. Okay, more or less is just a few more than half an hour, if I understood. Okay, right?
Yeah,
okay.
Something like that, I think.
So Hastlayer is right the pronounce?
Hastlayer, yeah.
Okay, more or less layer, liar. Okay. I give you the microphone. Okay, I'm adding also your PC. Okay, you see that are your slide, and good luck and make us feel like great programmers of this kind of let's say magic. Okay.
Thank you very much. And sorry, please let me know if there are questions in the meantime. So we needn't wait until the end with them. We can make this more of a discussion if the audience like to.
Perfect. Yes.
But let me get into this. And indeed, it's a bit like magic, but it's actually not magic. It's fully open source, so you can also deep dive into how this thing works, which is indeed our Hastlayer project. So let's see what the whole thing is about and how you as a .NET developer can turn your .NET programs into computer chips. Just a little bit of interaction before that. I'm from a company called Lombic Technologies. Day-to-day, we are doing web development with the ASP.NET Core framework and CMS called Orchard Core. We are the biggest Orchard Core team in the world. We are market leaders with clients from all over the world, including Fortune 500 companies like Live Nation or Microsoft itself, or institutions like the Smithsonian Institution. But when we are not doing research and development, or we are not doing web development, then we are doing some research and development like our Hastlayer project. Before talking about Hastlayer, though, let's talk about you. And let's suppose that you are doing some number crunching. And by number crunching, I mean that you have some kind of application, some kind of algorithm in the following areas. For example, AI, machine learning, pretty fashionable topics today, including large language models. Or you have some kind of high-performance algorithm in the areas of image or video processing, which to a degree are quite similar, or you work in computer vision, like you work with robots, even industrial ones, or surveillance systems. Or you do some algorithmic trading on the stock market, even high-frequency trading. Or data compression is an important part of your algorithm. Or lastly, you perhaps do something in the areas of cryptography or cryptocurrencies. Now, if you have an algorithm there and it's not fast enough, so it causes user experience issues, or it makes some business processes inefficient, then you want to make it faster. And there are certain things that you can make to make it faster. And as a .NET developer, there are some usual steps that we can take here. First, of course, you can figure out what is actually slow there. You can profile your application and try to optimize the slow parts. And now let's suppose that you have already done that. The second step it would be to parallelize that algorithm to make it multi-threaded. Because, you can make something very fast, but you have a lot of processor cores in your PC, so you can actually utilize them. Now, let's suppose that you have already parallelized your algorithm. And the last basic step you can take here is to, just scale up, use faster hardware, or scale out, use more hardware, more servers to run that application. Now, let's suppose that you have done this as well, or rather, you reached the feasibility limits. There's nothing more you can feasibly do because you can infinitely throw money at the problem, but at one point you get diminishing returns. It just doesn't make sense. So you have to figure out something else. And the next step here would be to use a heterogeneous computing approach. And that means that instead of processing something with the CPU of a server, of a PC, you use specific hardware accelerators like graphic processing units, video cards, or FPGAs. Now, let's talk about that last part a little bit more, heterogeneous computing. And FPGAs there, if you haven't heard of them yet, or field programmable gate arrays, are basically chips that can behave like any other computer chip, within limitations, of course. For example, if you want an FPGA to process the physics calculations of your computer game, you can configure it to do that. If you want it to recognize cats in images, you can also configure an FPGA to do that. Now, even if you haven't worked with them directly before, I'm pretty sure that in some way you have already used FPGAs. For example, if you Google something on Bing, then you are using FPGAs because Bing is accelerated by FPGAs. Similarly, Azure widely uses FPGAs for networking tasks. And sometimes FPGAs can also found in household appliances like routers and less household appliances like X-ray machines or self-driving vehicles. Now, there's one peculiarity to them though. To utilize FPGAs, you have to be a hardware engineer because, it's pretty much designing a chip, so you need to process hardware engineering knowledge. Now, to alleviate some confusion, is an FPGA the same as a Raspberry Pi? Well, no. Although a Raspberry is also some little computing thing that has a visible circuit board, no, that's a computer. Similarly, an Arduino or a NetDuino is something else. They are microcontrollers. That being said, sometimes FPGAs are actually built together with a Raspberry or a microcontroller. And now let's compare different computing devices a little bit. So let's see when are CPUs, GPUs, or FPGAs good and how do they compare. This is here just to give you a rough idea. So this comparison here is totally non-scientific, just a very crude approximation. And of course, the devil is in the details, so you can make arguments either way. But generally, this is how things compare. And let's talk about parallelism first, the chart on the left. Now, how many things you can compute at a given time. And the CPUs are, I would say, on the lower end here. So, on a CPU, you have something like 4, 8, 16, maybe 64 processor cores, but that's about it. GPUs, on the other hand, are highly parallel devices. They have thousands of little processing cores. Now, those are very different than CPU cores, but still, the hardware level parallelism you can get is a lot higher there. And FPGAs are roughly in between, I would say, because FPGAs don't really have cores, so to say, but the degree of parallelism you can get with an FPGA is roughly in the order of hundreds. And next, how about the complexity of programs you can run on these devices? And with CPUs, they win. If it's a piece of software, you can run it on a CPU. GPUs, on the other hand, are much more restricted. The programming model is very different there. You can't just do anything. And FPGAs are in between, I would say, although you are not running a program on an FPGA, but the algorithms you can implement on an FPGA are roughly in between. And last, talk about power efficiency. CPUs and GPUs, I would say, are roughly on the same level here, although this, again, highly depends on the details, but FPGAs really shine. FPGAs are highly power-efficient devices, and the reason for that is that they just compute what you need to be computed. Nothing else. There's no operating system, no other programs to run. There's not even an instruction set, like for a CPU or any other processor. It's just bare metal. Bare metal. Nothing else, just your algorithm. And, oops. And this is all great. There's one downside, though, because programming a CPU is easy enough. Programming a GPU is not much harder nowadays, but utilizing an FPGA is something completely different. You have to be a hardware engineer. It's super low level. You have to think in terms of wires and logic gates and clock cycles. You are not writing a program for a processor. You are kind of creating a processor for your algorithm. And this is where all the benefits come from, but this is all where all the complexity comes from as well. But with high-level tools like Hastlayer, we intend to bring this complexity down onto the software development level. Speaking of which, what is Hastlayer actually? Well, Hastlayer is a tool that takes a computer program and turns it into an equivalent FPGA logic. Or we could also say that it takes a computer program and turns it into an equivalent computer chip, kind of the tagline that's in the talk as well. Or Hastlayer tries to kind of get out the logic which was originally expressed as software form. It doesn't mimic the software, but it tries to get the logic out of it and then create some equivalent logic, which is expressed as hardware. And of course, we are at a .NET meetup, not just any software. We are talking about .NET software. And actually .NET, so not C# code, but .NET, because what Hastlayer processes are the .NET DLLs, the .NET intermediate language assemblies. And because of that, at least in theory, any .NET compatible language can be used, including Visual Basic, C++, or even function languages like F#, or even scripting languages like Python. So to summarize, what we are aiming for here is having all the benefits or the computing benefits of FPGAs for all of us software developers. So first, you can get a substantial performance increase for highly parallel compute bound or memory bound algorithms. Secondly, you also get a higher power efficiency. And the power efficiency, of course, is not just for power efficiency's sake, and it's good for the environment, but it's also good for your wallet, because we are talking about a reduction of costs, a reduction of computing costs. The cost driver when it comes to operating a data center is actually power, because first you pay for the power itself, for the electricity, and then you pay to dissipate that power to cool the data center. If you can reduce that, you can reduce the operating cost substantially. And thirdly, we are still talking about software development as usual. Not much special that you have to learn. Lots of talk until now. Let me actually show you how the whole thing works in action. So now I'm switching over to Visual Studio. And what we have here is a sample algorithm. By the way, everything that I show you here is up on GitHub. It's fully open source. You can check out all the sample projects in more detail. I'm just showing you one of those. And this one is kind of an exaggerated example of the kind of algorithms that you can accelerate with Hastlayer and with FPGAs. It's not a real-life example. And as you can tell from the name, it's a parallel, highly parallelized algorithm. So let's check it out in detail. What this does is pretty much here. This is the core of its logic. Again, it's not something that would make sense. This is a synthetic example. And what we have here is some code that emulates some number crunching. Because, there's some conditional logic and there's some number crunching. There's some loop that goes to 10 million. And what's more important is that this happens in tasks. Now, if you are not familiar with that, tasks are an abstraction over threads in .NET. You could basically say that we are running multiple threads here. But what's important is that we are not using these threads directly, but rather we let the .NET Task Scheduler do that. The .NET Task Scheduler will make sure that the whole thing stays efficient. And this is especially important because we start a lot of tasks. This many, actually. And this many is 260. So this starts 260 tasks. And now if you have a 4-core CPU, then those tasks will still run on those 4 cores. Just .NET will make sure that everything stays efficient, the CPU is not oversaturated. But what's more important here is that when we turn this code into a piece of logic hardware with Hastlayer, then these 260 tasks will actually be turned into 260 cores, hardware cores. So we'll get a level of parallelism on the hardware of 260. I will show you the whole thing in action in a minute as well. There's some further plumbing in this algorithm here, but nothing too important. So let's actually check this out in action. I will now switch over to a terminal. And the reason for that is that what I will use for this demo is this. Let me make a little bit more light here. Is this board here? And I wanted to show you something special. Hastlayer works in the cloud. You can also use it on premises in Azure, but you can also use it on board of a satellite or on board of a drone. And what I have here in my hands is actually the same hardware that goes on in the onboard computers of satellites too. This is a small FPGA, which is on the same chip as an ARM CPU, a 2-core ARM CPU. So this is a little onboard computer. It runs its own Linux, it runs its own .NET, and it runs Hastlayer. And this is why I use a terminal to remote into it. So let me switch back to the terminal, and let me start a demo script here. What this does is that it uses the same parallel algorithm sample. First, it generates the hardware implementation, and then it starts to execute the software implementation first. And once that's finished, it will start to execute the hardware implementation. We'll see the differences in a couple of seconds. Usually, you wouldn't start the hardware, you wouldn't generate the hardware on such an embedded system, but this actually happened in like 2 seconds here. That's why it's also included in this demo. Now, as mentioned, this little onboard computer has an ARM CPU with an FPGA. This is an ARM CPU quite similar to what you have in your smartphone. Most possibly, this is a slower one because this is a 2-core CPU clocked around 650 megahertz or something like that. But this is usual for such use cases and usual for satellites. So the whole thing finished. And here are the results. On the CPU, it took around 54 seconds to execute this parallel algorithm. Usually, it actually takes around half of that. I'm not sure why it's so slow today, but being uncertain in the execution time is actually also one of the aspects of CPU execution. And that's one thing that FPGAs actually solve, because with FPGAs, it's exactly the same amount of time every time. What we can check out next, if you scroll down a little bit and check out how long the hardware execution took. And we have the details of that here. And on the hardware, it took around 240 milliseconds if we just take the hardware execution itself into account. So this is the time elapsed on the FPGA chip. But of course, from the CPU, we also had to send data to the FPGA and receive that data back. So with that included, we are talking about something like 330 milliseconds. Now, since we are talking about .NET, there's JIT compilation going on and caching. So if we execute the whole thing again a second time, we see that the whole round trip is now just 245 milliseconds, not 300 something. So the whole thing got a lot faster, but what happened on the hardware itself is exactly the same amount of time. Exactly. So this is one thing that makes hardware execution very reliable. And as you can see, we are talking about even with the round trip around 250 milliseconds versus more than 50 seconds. So the hardware execution was about 200 times faster. That's quite a large speed up that you can get like this quite easily without actually knowing much about how FPGAs or hardware design works. And you may ask that, okay, we have seen this parallel algorithm sample, but that's just the algorithm itself. So in this run method, we have our algorithm, which runs in a hardware accelerated way. But how do we start this algorithm from the host PC? How do we integrate Hastlayer into our application? And well, this other sample here is about that. What we are watching now is the main class of a small console application, and this demonstrates you how to utilize Hastlayer. Well, first you create this such a Hastlayer shell, and then comes some configuration. A lot of this is optional here, but the most important, or pretty much in this section, the only important part is that we tell Hastlayer that the class whose objects we want to call from the host PC, from the outside, is this parallel algorithm. And then comes the hardware generation itself. This method call here is that creates the hardware implementation. And as you can see, we actually pass the corresponding assemblies to it as well. And then comes the execution. So this is where we actually utilize Hastlayer to execute the software implementation. And then which happens here. And then the hardware implementation below here too. And as you can see, the special thing here is that there's nothing really special. We just call this run method on this object, and pretty much that's it. There's a little bit of specialty here, though. You see, here is where we instantiate this parallel algorithm, and then we actually let Hastlayer wrap it into a so-called dynamic proxy. This means that Hastlayer will be able to hijack method calls going to that object and transfer the execution to the hardware. It can actually do this optionally. So depending on the input, you can even add logic to decide whether offloading it to the FPGA makes sense, or whether you actually want to keep the execution on the CPU. Sometimes, for example, if you are talking about an image processing algorithm, then if the image is really small, then we don't want to offload it because it will be fast enough on a CPU as well. It would be just too much overhead to send and receive to and from the FPGA. You can just do it on the CPU faster. And with larger images, you can decide on offloading them. So that was how you use Hastlayer. Now let me show you a little bit how Hastlayer itself works, because perhaps you may be wondering, it's okay, that's cool, but how is the sausage made? And this is it. This is the device that I've shown you via my webcam. This is the onboard computer itself, and it contains a chip called Zinc. That Zinc is that has an ARM CPU and an FPGA together. That's the little thing in the middle. And this whole little board goes into a larger board that I've also shown you, which is a motherboard for development. So this is not something that would be on board of a satellite, but this is what we use for development because it contains like Ethernet ports, ports for a power supply, USB ports, you name it, things that we need for development. And let me show you a little bit of the hardware itself, because what Hastlayer actually generates is code like this. What we are looking at now is a VHDL code file. VHDL is a hardware description language. What you see here is code, and it may look similar to a program because it has something called a function. This if-else looks like some kind of program as well, but this is not a program. This describes a piece of logic hardware. And even though some keywords are actually the same and some pieces of this look similar, it's actually very, very different. The end result here won't be an executable program, but rather it will be a piece of logic hardware. And if we scroll down a little bit more, we'll see something familiar as well. Parallel algorithm. So, you know, this is a name we remember. This has something to do with that parallel algorithm class. And what I'm showing you here, this block is a bunch of type declarations. This is not the logic of our parallel algorithm class, but these are just type declarations, much like having a list of properties in a class in C#. But why I'm showing you this is because if you check it out closer, there's an index of 0 to it. And if you scroll down a little bit more, we can see exactly the same thing with the index 1. And then again, the index 2. Now, can you guess where I'm going with this? Well, perhaps yes, because if you scroll down a little bit more, we can see the same thing again with the index 257, and then finally with the index 259. Now remember that in Visual Studio, in this parallel algorithm, we started 260 tasks, So this thing here was started in 260 tasks. Well, as I mentioned then, Hastlayer creates a 260 core processor for that algorithm. And this is what we see here. Here we have the 260 copies of our algorithm. Well, at least the type declarations here, but if we scroll down a little bit more, we'll see the logic as well. But that's very complicated and very long, so I didn't want to start by showing you that. And these 260 copies is where the computing benefits of FPGAs come from, because this way we get kind of like a 260 core processor just for parallel algorithm. It won't be able to compute anything else, but what our parallel algorithm class needs, it will compute very, very efficiently and very, very quickly. It's all the efficiency of parallelized computing and having specialized hardware, but you don't need to go to a cheap manufacturer, to get this manufactured, but actually you can just reconfigure an FPGA. What else do we have here? We support a technology called Xilinx Vitis, actually. Xilinx is one of the FPGA manufacturers, the biggest one out there, and they have a platform called Vitis. Vitis is a little bit like .NET for FPGAs in a way that it lets you support multiple FPGAs at the same time. It's not completely true like this, because with FPGAs, due to the intricacies of hardware development, you have to add support for each and every chip and each and every board. So that's still hard, but with Vitis, we at least support, well, first of all, high performance cards in data centers like Azure. And secondly, we also support such embedded systems like the one I've mentioned, which is available on board of drones and satellites. We also made some benchmarks. The details of these and all the numbers are also available on GitHub. And with the high-performance data center accelerator cards, we got numbers like these. The algorithms got around 4 to 30 times faster, consuming 120 times less power, which again is cost saved. We have also done some benchmarks with the Zing, so this onboard computer that I've shown you here, and the results there are actually even better. Now, keep in mind that it's hard to do such comparisons, because comparing a CPU with an FPGA implementation won't be fair, because these are completely different computing devices. We try to compare devices on roughly the same level, though. And when we are talking about the Zing benchmarks, we compared the FPGA of the Zing with the CPU of the Zing. So these are better numbers against itself, but the Alveo one were the huge FPGAs against huge and expensive server CPUs. A curiosity that you can also do with Hastlayer is having your own number formats. Now, perhaps that's not something that you do every day, but actually with machine learning, it's quite a frequent occurrence that you want to use reduced precision floating point. Smaller numbers that are still good for you, still accurate enough, but they are smaller, and you can fit more into memory or more onto some storage. And we actually created something like this called a POSIT. Now, POSITs, the number type wasn't invented by us, rather by a mathematician called Dr. John Gustafson. But what we created was a .NET library, pretty much a .NET struct called POSIT. And with that, you can use POSITs in your .NET software. why you do that is because POSITs promise to have better range and better accuracy with fewer bits, smaller sizes than the standard IEEE floats that we have as double and float in .NET. And since this was made in a Hastlayer compatible way, actually the whole thing with the push of a button is available in a hardware format as well. So we kind of created a number format and at the same time a processor that supports that number format. We want to have more use cases for Hastlayer. So if you have them, please let me know. I would be more than happy to talk about that, to see whether Hastlayer is actually suitable. This is why we also got into a partnership with the Wigner Research Center for Physics to test Hastlayer on physics computations. And be ready, because FPGAs are quite available nowadays. In all major cloud providers, you can use FPGAs, like AWS, Azure, as mentioned, has FPGAs. And the two big CPU manufacturers also acquired FPGA manufacturers. Namely, Intel acquired the then second largest FPGA company called Altera, and AMD more recently acquired the then largest FPGA company called Xilinx. And as mentioned, while to my knowledge, ARM is not creating anything with FPGAs themselves, still, as we have seen seen on the example of this onboard computer that I've shown you here, ARM CPUs can also be coupled together with FPGAs. So to wrap things up, if you like this, and I really hope you did, then please go on GitHub and check out the SDK. Everything that I've shown you today and everything else that you need to run Hastlayer is up on GitHub. And be ready, because I think FPGAs are coming. Just as in the very beginning, GPUs were more like the playground of specialists, this is how FPGAs started too. But just as eventually we arrived at general purpose GPU computing and everyday GPU acceleration outside of video games and graphics computations, the same shift is happening with FPGAs. FPGAs are also becoming general purpose compute accelerators. So feel free to get in touch with me if you have any questions or any further feedback. And now we can also have a discussion if there are any questions right away.
You finished, Zoltán? I see the glass of water that is typical in this case, right? Or we stay just with your contacts here. So Zoltán Lehóczky.hastlayer.com. But if you remember Hastlayer, I think that also in the site we can find your mails, right?
Yes, and I will also send a message under the meetup even.
We can come back just we two, okay, Zoltán. I remember that maybe we met some years ago. I was in a meeting room with Mauro that was hosting you, but I think that have passed 5 or 6 years, and I heard a lesson like this one. I don't know if Hastlayer was already being invented or not, and you only talked about FPGAs, is right? Or my memory is joking now?
I believe, yes, that indeed happened.
Yes.
And indeed, something like 5-6 years ago, I also toured such meetups and other events with Hastlayer in a very early form, of course. That wasn't nearly as advanced and polished as today. But yes, indeed, that was the case.
Was already with Hastlayer or not in that case? How long is Hastlayer been, let's say, growing?
It should be. I think it was Hastlayer, yes, definitely. We started the project in earnest 2016, I think.
So was in the beginning, okay, let's say, or was your first presentation of all? Because I remember that and I was very surprised of this piece of hardware that was so fast. Now something has changed. Okay, I want to ask you what can happen with the let's say AI connected to this kind of speeding. Okay, hardware speeding. What are the goals, and what is your vision about FPGAs and join to this?
Usually when we are talking about AI, we are talking about neural networks in some form. The large language models of today are largely neural networks as well. And when it comes to neural networks, it's all about floating point matrix computations. GPUs are very good with that, so that's why GPUs were used to accelerate AI workloads to begin with. And usually that's what AI accelerators nowadays do as well. Now, FPGAs have strengths somewhere else, but so they can do that as well. But usually you would use an FPGA when it's not just about raw floating point matrix computations, because GPUs are the best there. Or AI accelerators when you are looking for that kind of workload specifically. Hastlayer and FPGAs can help if you want to accelerate a bigger part of the algorithm, especially if it's custom, and especially if you are using custom number types as well, as I mentioned with POSITs. So when it comes to hardwired chips, the number types need to be supported in the hardware for them to be fast. So when you are using a number with the type double or float in .NET, your CPU in your computer actually knows that number type. It has little pieces wired in just for that number type. But if you want to use some more efficient number type, so you can, for example, fit a larger piece of that large language model into the memory of a server, then you are usually out of luck. And that's one of the aspects where FPGAs can help.
Okay. Let's say, Zoltán, I go to my boss and I say, oh, I've seen a great speech by Zoltán Lehóczky about FPGA and also Hastlayer. Okay. Given that Hastlayer, I think that it's quite easy to use. We have seen that it is not, there is a SDK, and I know that maybe it's deep, but in the general manner, it's quite easy. How can a developer start with FPGA? He has to go to a computer shop to take one of those, or as you said, we can find several kind of applications on Azure or AWS and so on. What's the name of it? There is a feature to click to use FPGA in the backend. How it works?
So the first step would be to check out the documentation of Hastlayer. That's also available on GitHub, so under that SDK link that I'm showing now too. And from there, you can explore the options. And indeed, the easiest would be to use a cloud provider. So this is also elaborated in the documentation, but you can go to Azure and pretty much rent a virtual machine with an FPGA by the hour, just as you would do with any virtual machine.
Okay, virtual machines. Okay, perfect. I am showing again the GitHub link and also other links. Perfect. Okay, understood. Zoltán, for me, it's enough in the meaning that there is of course, a very new item to know. Okay, more than Hastlayer itself, it's all the FPGA world. Okay, thank you so much for giving us this opportunity.
Thank you.
Okay, and thank you for your time. Okay, and congratulations for this kind of let's say middleware. We can talk about middleware, about Hastlayer, or translator. What is the category?
Well, there's no specific category. We tend to call it a hardware accelerator for .NET.
Okay, perfect. Zoltán, goodbye. Thank you so much, and thank you to all our followers and all people of Torino.net Meetup. Thank you so much, and bye. See you next time.
Thank you very much. Bye, everyone.